When you have a concentration versus time graph, you should immediately be thinking that there are really only two useful things you can do with it. One is if they ask you for what the actual rate is at any point in time, you can draw a tangent and measure its gradient. But it hasn't asked you to do that here, it's asked you for the order of reaction. And so what you should think is half-lives. Look at the pattern for successive half-lives. So in this case, starting concentration is 2 times 10 to the minus 3. Notice the 10 to the minus 3 there. So starting point is 2 times 10 to the minus 3 moles per dm cubed. So we look for how long it takes to drop to half of that value. So we draw the line on. So you just draw a straight line across there till it clips the graph, and then we drop a line down, and that distance is the first half-life. It's really important that you mark this clearly on your diagram, because you get the credit not just for getting the right answer, but for showing clearly how you got it. And that means you've got to have the construction lines clear on the diagram, and you've got to mark on what the half-life is, and crucially you've got to state its value. Now on the original paper, you could see that it was actually slightly more than 0.9, so I would have put down equals, my estimate of 0.92 seconds. If you rounded it to oh God. If you rounded it to 0.9 seconds, that's probably okay. But if you can see with a bit more precision than that, then put it to a bit more precision than that. So that's about 0.92 seconds. And then you look for the second half-life, which is the time for this to halve again. So you mark another line across, whoops, with your ruler, drop it down, and again mark on what the second half-life was. Now that doesn't mean the time from the beginning. That's the common mistake. The second half-life is the time from the end of this one to there. So if you mark it on like this, get used to that, that will make that clear. So the second half-life is not 1.8 seconds. It's the difference between 0.9 and 1.8, which is again about 0.9 seconds, or again if you looked at it slightly more carefully, it comes out again about slightly more than 0.9, so about 0.92. So here's second half-life is again about 0.92 seconds. You can mark on another one if you want, time to drop from 0.5 to 0.25, but to be honest there's no point, because you can see the pattern just from that. So what you then say is successive half-lives are constant, okay, because each of them is the same value, and therefore it's first order with respect to the hydrogen peroxide concentration. So the things they're going to look for are the clear construction lines, that you write down the actual values of the half-lives and mark down clearly on the graph what they correspond to, and then draw the conclusion that because successive half-lives are constant, it's a first order reaction. If they'd been slightly different, so if you say you'd got 0.92 and 0.89, you would still say, well, they're approximately constant. If it was something different, like a second order reaction, the half-lives would double. Okay, so we're not looking at small increases here. So long as they're more or less the same number, then you can say, yeah, that's first order. Okay, so now on to part 2. So we know from the first part that the order of reaction is first order with respect to hydrogen peroxide. So the rate equation always has this form: rate equals K times the concentration to whatever power. So in this case it's power 1. Don't write in the 1. Anything to the power 1 is just itself. So it's just rate is equal to K times H2O2. So that gets you the first mark. And then it asks you to find the value of K. Now there are two ways to do this. The quick way is to recognise that because it's a first order reaction, and only because it's first order, you have this special relationship, which is that K is equal to log 2. So that's the natural log of 2. You should be able to find that function on your calculator. So it's just a number, the natural log of 2, divided by the half-life. And because it's a first order reaction, the half-life is constant, so it is what it is. So in our case it would be log 2 over, well, I measured 0.92, but whatever value you got, it would equal to that, and you just plug the number into your calculator and that should come out somewhere in the region of 0.75. Remember, it's going to have units, and for a first order reaction you may have learnt by now that the units work out as seconds to the minus 1, but it's important that you learn the general recipe, and the general recipe for the units of K are that it's moles to the 1 minus x, dm to the 3x minus 3, seconds to the minus 1. You need to learn that because it's extremely useful. Now in this case it's very simple. X is the overall order of reaction, so it's the sum of the orders for each of the individual reactants. In our case we only have one reactant and it's first order, so X is 1. So we get moles to the 1 minus 1 is 0. Now anything to the power 0 is just the number 1, so it's 1. This number is also 3 ones are 3, minus 3 is 0, so it's 1 times 1 times seconds to the minus 1, and so the unit is just seconds to the minus 1. Now using that relationship with the half-life is much the quickest way to do this, but there is an alternative, which is to rearrange this equation to solve for K. So if we just slide the H2O2 over to that side, we get rate divided by H2O2, concentration is equal to K. And these are both numbers that we have access to, because we can measure the rate at any particular hydrogen peroxide concentration by drawing a tangent on the graph. So one alternative approach would be to do that. So let's say, for example, that we're going to choose a concentration of 1 mole, or rather 1 times 10 to the minus 3 moles per dm cubed. So what we can do is draw a line across there so that it touches the curve at that point, and then we have to draw a tangent to the curve which just touches it at that point, and the gradient of that tangent is going to give us the rate. So with your ruler you're going to try and draw a line which just about touches the curve at that point, which would be something kind of like this. Okay, so you would then measure the gradient of that tangent. So gradient measuring is an important skill. You get to use it a lot in chemistry, and so make sure you know how to do it. Okay, so to get the gradient of a line, in this case the tangent that we've drawn, you have to remember what a gradient is, which is the vertical change divided by the horizontal change. So if you like, delta y divided by delta x. And you just have to read those numbers off the graph and plug them into the recipe. So the vertical change starts at around 1.6 on this axis and goes to 0, but we've got to remember this, that these numbers have been divided by 10 to the minus 3. So actually it goes from about 1.6 times 10 to the minus 3. Okay, because they had been divided by 10 to the minus 3, you've now got to multiply by 10 to the minus 3 to get the original number back. So it started about 1.6 times 10 to the minus 3 and goes down to 0. So the vertical change is 1.6 times 10 to the minus 3. The horizontal change, no correction on these, so we can just read it straight off. It goes from about 0 to 2.3. Okay, which comes out around 0.7 times 10 to the minus 3, or 7 times 10 to the minus 4. Is the number, and that's the rate, so that has units of moles per dm cubed per second. And we can then plug that into here and say, right, that's the rate. The concentration is the concentration at that point where the tangent was taken. In other words, we chose it to be 1 mole per dm cubed. So we can therefore say that K which is equal to the rate, divided by the hydrogen peroxide concentration, is equal to about 7 times 10 to the minus 4 divided by 1 times 10 to the minus 3. Again, remember the factor. It's not 1, it's 1 times 10 to the minus 3. So 1.0 times 10 to the minus 3, which comes out around 0.7. And again, it will be units of seconds to the minus 1. Okay, so that's the alternative way to get the value of k. You can see it's a lot more effort, and it's likely to be less precise because of the problem of drawing accurate gradients. So try to remember the log 2 divided by the half-life method for first order reactions, but this is a valid alternative. 3, we've got to check out whether John Bon Jovi's scheme is any good. So we've got to fit these two bits of information. We know the overall equation for the reaction, and we know the rate. Notice that in the question, the overall equation was just given as 1 H2O2 goes to H2O plus a half O2. When you're thinking about mechanisms, you can't have halves in the equation, because in mechanism equations we're writing about what happens to individual molecules, remember. Normally halves are fine because we're just talking about half a mole of something, which is not a problem. But if you're writing equations, as you are when you're talking about reaction mechanisms which relate to what individual molecules do, you obviously can't have half a molecule. So I've just doubled that up to get rid of the half, because that would have to be what went on at the individual molecule level. So we've got those two bits of information, and what we've got to do is to see whether this scheme works in terms of both of those. So first of all, to see if it fits the overall equation. To do that, all you have to do is simply add up everything on the two sides, write the overall equation at the bottom and do some cancelling. So you can see on the left hand side we have 2 H2O2s, we have 2 OHs, we have 1, 2, 3 HO2s, and that's it on the left hand side. And on the right hand side we have 2 OHs there, and that's it. So 2 OHs. We have 1 water, 2 waters. We have an HO2, just one of those on this side. And we have an H2O2. And we have 2 O2s. So there's quite a lot to keep track of, but if you just go through and count up everything, that's what you should get. And then there's going to be some cancelling to do, because lots of those things occur on both sides. Remember, you must never ever leave equations in that state where they have the same thing on both sides. We've got to go through and do the cancelling. We've got 2 H2O2s on the left, but one of them is still there on the right. So that cancels down to 1 H2O2, and we lose that one. OHs, you've got 2 on the left but also 2 on the right, so those cancel completely. And the HO2s, well, we've got 3 on the left but one of them appears on the right, so that cancels down to 2 HO2s, and that one cancels out. So what we end up with is H2O2 plus 2HO2 goes to 2H2O plus 2O2. And you can see that there's a problem there. It does balance, but it's not the right equation. So straight away, John's scheme's no good, because it doesn't, when you add it up, add up to the overall reaction. So that's the first flaw with it. The next question is, well, what about the rate equation? And in order to look at that, we have to take notice of the other information we were given, which is that that step is fast, that step is slow, that one is fast, and this one is also fast. So the principle we're working with, which is a really, really important one you've got to make sure you remember, is that the number of molecules of each substance involved in the rate determining step is equal to the order of reaction for that substance. And when the slow step comes first, that's easy because the slow step then is the rate determining step. And so you can then just say, right, the number of molecules involved in the slow step should equal the order of reaction. But when the slow step doesn't come at the beginning, that's not quite the same. So what we have to do is to say, right, what determines the rate is everything that happens up to there. In other words, up to and including the slow step. The fast things that happen afterwards, those don't really influence the rate. So what we do is we add up those two equations. In other words, you add up all of the equations up to and including the slow step. And that gives you, if you add them up, 2H2O2 plus OH. Sorry, no it doesn't. Okay, let's just re-record that. Let's edit out that little bit. So that adds up to, we've got two H2O2s on the left. We've got an OH there, but notice we end up with two OHs on the right. So that's going to cancel out, and therefore all we have on the left is two H2O2s. And then on the right hand side, we've got just one OH, because the other one was already there on the left, plus water, plus HO2. So that's the sum of those first two steps, and that effectively is the rate determining step, or the sum of those two steps. So the orders of reaction should equal the numbers of molecules on the left-hand side of that equation. And you can see that because that's the effective, this equation is the effective rate determining step, which means that it predicts that it would be second order for H2O2 because there are two of them reacting, and that's not what we observed experimentally. So it fails at both tests. It doesn't add up to the right overall equation, and it doesn't predict the correct outcome in terms of order of reaction because it should have been first order, but the sum of those two steps up to and including the slow one had two H2O2s, so it would then have had to be second order. So John was wrong.